Welcome to the AI for Predictive. I'm hosting this seminar series. Also, one small note here. To those who are the first time at this seminar series, I would like to mention that the RISE is organizing a seminar series with interesting external speaker every 2 weeks. So please feel free to share this seminar series within your network if you believe that someone is interested and get some benefit from this seminar. So we have today we are honored to have a speaker from Zurich University of Applied Science, Switzerland, Dr. Lila Goren-Hober. Please, Lila, excuse me if I pronounce your name is wrongly. Who will share her work on the topic of condition-based maintenance for energy system, a scalable deep learning algorithm using operational data. Dr. Lila Goren-Hober received her MSc and PhD in physics from the Weizmann Institute of Science in Israel. Since 2013, she is a senior scientist at the School of Engineering of Zurich University of Applied Science in Switzerland. Her research focuses on algorithms for intelligent maintenance and operation of technical systems. In recent years, her focus shifted toward machine learning and deep learning algorithms for the condition-based maintenance in various applications. So, on general information, the presentation will take around 30 to 45 minutes. Afterward, we'll have the opportunity for question and answer. As usual, we record this seminar, share it within our network, and also it is available on YouTube. And you can still watch the workshop seminar series afterward or offline if you miss it. So once again, welcome Lila. Now you have the floor and we are excited to listen your talks. Please go ahead and share your screen now so I can, please.
Thank you very much. So I will be sharing my screen. Please let me know if you see that.
Yes.
Okay, just one question on my side. I usually prefer it when people ask questions, when the discussion is vivid, also during the talk. Is this okay with you? I know you're recording, so maybe you want to say what your preference is.
Oh, I think we are fixable with both ways. It should be fine. So it's okay.
So I encourage people to interrupt me. I don't always see your hands. I don't have access to this, so please interrupt by just raising your voice and not your hand if you want to ask a question. So thank you very much for this nice introduction and for the invitation to present to you some of the work that we've been doing. I'm sorry for this. Some of the work that we've been doing in the last couple of months or years, actually. So with focus on energy systems this time, and how we actually aim at working together with industry partners. That's our daily job. And scaling up algorithms based on machine learning and deep learning for systems that are intrinsically based on operational data and not on any other tools that might be available for the academic community, such as laboratory experiments or synthetic data. So before I start, maybe let me introduce some of the people that are behind the work that I'll talk about today. What I will tell you today was mostly done by Yannick and Marcus, my research assistants that worked in the projects that I'll tell you about today about energy systems. But our team of smart maintenance at the Zurich University of Applied Sciences has been quite quickly growing in the last year, actually. And mostly what we notice is that we are kind of special in the sense that we are either physicists or engineers that also acquired a lot of knowledge in data science, and this intersection and this intercept between engineering and data science is exactly what a lot of companies in industry and in the public sector really need at the moment when it comes to predictive maintenance, smart maintenance, and operations of technical systems. So that's a lot of the directions that we're taking up recently are mixing very intentionally both physics and advanced methods from data science. And that's also partially what I'm going to tell you about today. So as I said, as an applied University for Applied Sciences, what we're doing is collaborating with partners from industry all over, usually Swiss industry, but also international industry and the public sector. And we're working together with them to find, to develop innovative solutions based in recent years, more and more data-driven innovative solutions in order to implement smart maintenance solutions in their systems. And one of these, the main sectors that we've been focusing on, we noticed that there is a very strong request coming from the energy sector in recent years. And I think I could point out a couple of reasons why energy systems are interesting and relevant for operations and for smart applications for efficient operation and maintenance. I think one of the reasons, which probably is obvious, is we're talking usually about high risk and high cost systems where failures or downtimes are very quickly accumulating a lot of cost consequences. So every downtime is lost energy. Every lost energy is has direct implication on the cost efficiency of the systems. Another aspect is that energy systems tend to be of very high technical complexity. They contain many times multiple subsystems. So a wind turbine in itself is a very complex structure. And also photovoltaic systems are complex, many subsystems that require detection and diagnostics that might take time if it's done manually and can be very efficiently automized. Also in these systems, operation and management adds up to a high fraction of the entire cost of energy. One example, one figure that I saw in the literature is that for wind turbine, it sometimes can get to 30% of the cost of energy that is spent on operation and management because of the high risk and because of the severe consequences of a failure. And often we're talking about systems that have huge quantities of historical data that accumulate over the years. For example, the SCADA system of wind turbines accumulate data sometimes over decades, which is mostly used to monitor the operation and only rarely used directly for the purpose of efficient maintenance schemes or maintenance applications. So it's only a matter of time until more and more operators and not only OEMs want to take advantage of these huge quantities that accumulate in order to also make their maintenance more efficient. Another point is the scaling potential. We're talking about large scale systems. We're talking about grid scale systems, both in case of wind turbines and in case of photovoltaic plants. We're talking about systems with units that repeat, or almost identical units that repeat maybe hundreds of thousands or tens of thousands of times, where manual processes are very inefficient. So it's very tempting to automate this kind of decision making. And last but not least, I think that because renewable energy, and I'm talking now mainly about renewable energy solutions, is in itself a rather new field, a rather involving innovative technology that keeps changing and keeps evolving very quickly in time, these industries have the tendency to be very susceptible to innovation in general. So have the tendency to accept very willingly innovative solutions that are based on data. So all this makes, for me, I think if you have more reasons that come to mind, I'm glad to discuss them, but make an ideal business case for condition-based and predictive maintenance when we're talking about grid-scale energy systems. So that's for the motivation for what I'm talking about. And now to a bit a different perspective about this motivation. So I've told you that we want to develop algorithms for smart or intelligent maintenance. And you must know, having heard maybe a series of seminars about AI for predictive maintenance, that the literature is full of such algorithms. The main problem that is also pointed out by people who are very, very experienced in this field is that actually taking these algorithms that are suggested in the scientific literature, machine learning and deep learning algorithms, and implementing them in real operational system poses a completely different set of challenges that is usually many times ignored when you're reading the scientific literature. And these type of challenges, we are forced to deal with them when we're working with our industry partners. So I think it's interesting to take a look at this angle, at this type of challenges that enable eventually real implementations, real applications of deep learning to survive in this field of smart maintenance, of intelligent maintenance solutions. So I'm going to put a little bit of the focus of this talk today about this gap, this challenge of transferring from research on one hand to real operational industrial systems on the other hand. And I know that this is for the RISE Institute, it's a very common, very usual way to look at things. So I would be happy to hear your opinion about that later on. So with that said, on general terms, I would like to dive now to one specific example, and later on to another specific example, where we actually, in a project that already ended recently, where we applied fault detection and isolation algorithms, that's FDI, for wind turbines. This project was financed by the Swiss Innovation Agency, and that's actually a very useful platform that we have that encourages collaborations between applied research and industry. And in this case, our industry partner was the company Fluence. Actually, back then, it was not called Fluence, it was called Nispera, and it was a startup. But since then, it was purchased by a big player in the field who's called Fluence. And maybe one of the reasons for this purchase was because Nispera was never afraid to be innovative. And what we developed together with Nispera is a new platform, a new tool, software tool for predictive maintenance. So Nispera has a platform for data analytics for renewable assets. They're working mainly with wind turbines and with photovoltaic plants, and they're developing the entire data analytics platform for all the purposes that you can think of. And one of these purposes was to develop now an add-on to offer their customers with a predictive maintenance software module. And this software module already exists, and for a long time now, actually, and is being sold to customers. So what I'm telling you about today is really something that ended up being a product. And this project was also in collaboration with EKZ, that's the electricity utility of the canton of Zurich, that helped us elaborate the use cases and validate our algorithms. So now the motivation of our industry partner, of the company, was to come up with predictive maintenance or condition-based maintenance algorithms that are based exclusively on data that has already been lying out there. without the need to install any new hardware, without the need to perform any lab experiments or to acquire data from other sources. And the data that was already there was the SCADA data. As opposed to what some of you might be familiar with, this is not the high-frequency vibration data that the original equipment manufacturers have. So the OEMs, they usually have access to vibration data, monitoring directly the activity of the bearings inside the drivetrain of the turbine and so on. Nispera, and its customers are the operators of the wind farm, do not have the access to this without paying extra money to the OEM. And in order to get information which is independent from the OEM, to disconnect themselves from the OEM, they would like to have direct information about failures, about incipient faults in the system without the need for any new hardware. So based on exclusively on existing data from the SCADA system, the supervise and control and data acquisition system, which records data with a time resolution of 10 minutes only. This is explicitly a low frequency data. So talking about vibration spectrum is not relevant here. And all the methods that are related to vibration spectrum are not relevant here. So we have to come up with our own algorithms that are based only on the available data from the SCADA system. And our purpose is basically to take the existing data, the historical data, and to train algorithms. And the existing data includes both environmental variables like the wind speed and the ambient temperature, but also performance variables and temperatures of components inside the wind turbine. And the purpose is to take this time series data, this sensor data, and to come up with a fault detection, first of all, a fault detection algorithm that eventually can also be used for isolation to tell us not only that there is a fault, but also where the fault is. And we are focusing on the specific set of faults that is related to the temperature variables of the drivetrain. So we explicitly focus in this project on the low-hanging fruits of how do I discover that there is an incipient fault that manifests itself by heating up of one or many components inside the drivetrain of the turbine. Is this clear to everybody? Do you already have questions about the use case that I'm focusing on? Please interrupt me if this is the case. Okay, I see no reaction, so I'm going on. Sorry. Okay, so here there's already some kind of a gap between what we are used to from the literature on deep learning and what we have to deal with currently. And this first gap is usually we would just pick, in order to detect whether a sensor data is healthy or faulty, we would just use a classifier. We would show the classifier, we train the classifier with both faulty and healthy data, and we reach the conclusion whether when the algorithm is properly trained, the algorithm would tell us if we're dealing with healthy or faulty data. And now, of course, this is not the case when we're talking about fault detection, because fault detection inherently in industrial systems, we almost never have labeled faulty data, or very little faulty data which is labeled, which is known in advance, and it might not be representative of all fault types. So of course I have to resort to the family of method known as anomaly detection. In anomaly detection, I'm training my algorithms with healthy data only, and I teach my algorithm what to expect from a healthy system such that it knows eventually to monitor deviation from normality. So this is, I guess, is familiar to most of you. And this is indeed what we did in the first step, implementing anomaly detection algorithms for the wind turbines. So first step is to take the historical database, to select appropriate training data, to train our machine learning, in this case, deep learning algorithms with normal data, with healthy data only, and to to train them to predict variables of the system that are being monitored. So to train them to predict, for example, temperatures of different components of the turbine. Let's take as an example the generator bearing temperature. So I train my AI to be able to predict how the generator bearing temperature would look like for a healthy turbine. And then I go and compare the prediction, the expected normal temperature, with the measured temperature. And whenever I discover deviations, strong deviations, I raise a flag, I raise an alarm, I trigger an alarm, and I say, here, there might be a fault developing. Is it clear until now? You don't disturb me, then I guess it is. Okay, so, and then the next step is after I did that, and it turns out to work very, very well for single components like the generator bearing temperature. And this is actually a matter that I won't have time to dive into what algorithm exactly we chose. In this case, it was a convolutional neural network. And it worked very well and could anticipate faults 2 to 6 weeks in advance and allow the time to respond, to intervene, which would exactly be answering the question of early fault detection. And now we're taking a step further, which is how to actually scale that up to a multi-component system. Because until now, I only talked to you about the generator bearing temperature as a single output variable, as a single prediction variable. And now I want to scale that up without making a lot of computational effort. I want to scale that up to a multi-component system. And then the question is, do I really have to train for each and every component a separate CNN that would do that? In our case, it's a one-dimensional CNN. And the answer is no. And the way we solved it is that we actually trained a multi-output CNN that could predict at the same time a multitude of variables, in this case, a multitude of temperatures for different components of the turbine at the same time. And this is how it looks like. So it produces basically such a dashboard. And in this dashboard, what you see is basically the residuals of the prediction. When the residual of the prediction, residual is the difference between predicted and measured. When it's small, it's colored with blue. And when it's high, it's colored with red, which signalizes a fault that might be developing. And of course, there is the question of how to set a threshold, and all these questions we dealt with, but I don't have time to get into. If you want to know more details, this is the publication you should look at, or ask me questions later on. I'm happy to answer questions. But what you see here are basically the health indicators or the fault indicators, if you want. Whenever the indicator grows and becomes red, we know we are encountering a faulty situation in one component or more. And the entire picture of looking at 10 components at the same time, and actually even 30 is possible, takes us in the direction of diagnostics. So it gives us a way to not only identify that there is a fault, but also localize the fault within the big system and say which components are related to the fault. So, and an important thing to stress here is that computationally, we almost did not pay any price. So training the single output network and the multi-output network cost computationally almost the same, and yields in terms of the robustness and the fidelity of the results, yields almost the same quality of results. So if we compare that, this is for the experts that know what I'm talking about when I say multi-layer perceptron. So a fully connected network with the CNN with one output and with the CNN with multi-outputs, we see that the fully connected network performs much more poorly than the two CNNs, and that the two CNNs are close to each other, even if I take one of them is outputting at the same time 10 different outputs. So this is a very satisfactory result that allows us to scale up the deployment of these algorithms to multi-component systems. So now this works very well for a single turbine. And the next step, going beyond the single turbine, is scaling it up to heterogeneous machine fleets. Or in our case, looking at the level of wind parks and of several wind parks of the same owner, and being able to use the same algorithm all over the place. And without getting into a lot of technical details, the way we solve that, not surprisingly, is, sorry for this. Do you see my screen, or do you see the message now? Sorry.
We can see your screen and the message.
And the message. Okay, so let me try to get rid of the message. Sorry for that. Okay, I'm sorry for this. So without getting into too many details about the technique, the way we solved it is, not surprisingly, transfer learning. The idea was, in order to avoid training a separate CNN for each turbine, we would like to train on one turbine and to deploy the algorithms on all of the other turbines in the same park, and eventually also outside the same park, which is the second part of this paper. But if we just limit ourselves for a second to scaling up from the turbine level to the park level, a very simple approach of transfer learning already does the job very well. And the way you see it, and the message that you can take from this slide, is a comparison between left, applying transfer learning, and right, training from scratch on each and every turbine separately, the same CNN. And because the differences are very small, we concluded, and we measured that, of course, we quantified that in the paper, we concluded that transfer learning is a very good method to scale up the training in this case. Instead of retraining for each and every turbine, which would be costly in terms of computations, we can train once and only transfer the information to all of the other turbines in the park using a very simple technique of transfer learning in this case. And so maybe you have questions until now before I switch gears to yet another technique. Okay, so
I have a question.
Yes, please.
Sorry. Yeah. So in your CNN model that outputs several variables, is there a guarantee that observing a large residual in one variable corresponds to having a fault in that particular component?
It's an excellent question, because it's not the case. You might be very informed and very experienced with autoencoders asking these questions, because this is, for example, not the case using autoencoders. However, because we chose a network which is based on regression and not on reconstruction, we avoided the problem which often occurs in autoencoders and would have occurred in this case also, of redistribution of the residuals between the different outputs in a non-physical way. In this case, because it's a one-way regression with inputs that are independent of the fault and outputs which are affected by the fault, we can guarantee that whenever a variable shows a deviation in its residuals, this is a variable which is affected directly by the fault. So, and this is not the case using reconstruction methods. So I will say a word about that at the end of the talk, but I actually gave a tutorial about that 2 weeks ago in the PHM in the US, and the tutorial is online, including also a code which is available. If you Google PHM Nashville, you will find it. And there we elaborate exactly on that point. So you can remind me later on, but I have the link also in the presentation, so you will find it. Did I answer your question?
Yes, thank you. And I saw your tutorial in Nashville. It was really good.
Thank you very much. Okay, so there we really answered this. So, right, exactly. So now I switch to another point, which is what do I do with limited data, which is not only faulty. So in a scenario, and this often happens for wind turbines, in a scenario in which I am forced to use very little healthy data for training because maybe my turbines are just newly installed or just had a renovation or a renewal of some components, and I can forget about using the past historical data, and I start accumulating data, and I ask myself, okay, starting from when can I actually deploy my algorithms? Is 1 month of data enough? 2 months? 3 months? How long do I have to wait until I can deploy my algorithms on new machines? And here we came up with several solutions. One solution was in terms of transfer learning, and that's the one I talked about in my tutorial also. And here I have another idea for how to deal with that, and it works very well for wind turbines because they kind of bunch in terms of the fact that they all experience the same environmental conditions. So it makes sense to actually gather the information from all the CNNs. So to train the CNNs, in this case, using training one and using transfer learning for all the others, for examples, or just training all of them if you really don't care about resources, and take the prediction errors or the residuals of the single ones and then combine them in a smart way. And this is what we did, and that's in another paper that you will soon see the reference to. Combine them in a smart way such that you could actually train with very little data. So what happens if we, in this case for the wind turbines, if we train with just winter data? The obvious scenario is there. So if we train only with winter data, we end up having false alarms during summer because summer conditions are not known to our algorithms and it interprets them as anomalies. So all these red points here in summer are interpreted as anomalies. These will be false alarms. And false alarms are the one thing which is worse than not detecting faults. Just sending people to the field without any reason, especially when we're talking about remote wind turbines, this is unacceptable. So we have to find a way to get rid of these false alarms every summer, even though we can't afford, we imagine a scenario in which we don't have any access to more than just winter data. And the way we did that is by combining the information of these 3 months of data, which is now training also very quickly because it's only 3 months of data, combining all the turbines together. And this is what happens when you combine all the turbines together. You still get huge residuals, but you know to interpret them not as potential faults. So you basically come up with another way of extracting your alarm thresholds. And that's the idea behind this method. That is a fleet-based method to come up with smarter anomaly scores. So, and again, for more details, more technical details, this is yet another publication that we had in the past. So what we see here is that now we basically saw several problems that we had to tackle while scaling up our solution to real operational conditions that most probably if we worked with the synthetic data, we wouldn't even think that this might be a problem. But the realistic scenario forced us to deal with all these problems and find ways to deal with them, which we believe are more than just specifically valid for this system. And this is why I'm actually telling you about that. And now I go back towards the end. Now I would like to go back to the question that I mentioned at the beginning, which was what do I do in a system where I almost don't have faulty data, labeled faulty data. And one approach would be, okay, so do anomaly detection and train with healthy data only. Another approach would be to actually use our knowledge, our physical knowledge of the system in order to augment the data that we have. And this is what we did for photovoltaic plants. So that's a completely different approach to dealing with the fact that we have limited faulty data, and using the fact that we actually have lots of physical and engineering knowledge about the fault mechanism. And one option would be to build a system simulator from A to Z to simulate the healthy behavior and then to induce faults into the simulator and simulate also faulty behavior. The second option would be, okay, we have already operational data from the healthy regime. So let's use the operational data from the healthy regime and benefit from the fact that we have lots of physical properties already accounted for in this healthy data, and only introduce the faults into the healthy data by means of understanding the fault mechanism. And the advantage of this option 2 is that we don't need a complete and accurate model of the entire system, a full simulator, and we can cover complex unknown mechanisms that we don't know how to model, but the field data models them for us. And in order to understand what I mean by that, let me give you the example of how we solved the problem of detecting tracker faults in solar panel, in solar energy plants. So I'm talking again about large scale plants, and again about a project, another project with Fluence, this time with another partner that operates the plants. And here it's all about fault diagnostics in grid scale solar plants. And tracker faults are only one failure mode that can come about here. So there are many different failure modes, and eventually our goal would be to be able to tell between them. But for now, let me focus only about tracker faults, and imagine that the entire goal now is to detect tracker faults and no other faults in the system, only the tracker faults. So what are the tracker faults? The trackers are those installations on which the photovoltaic panels are mounted, and the trackers allow the panels to rotate such that they can optimize the radiation absorption from the sun. And this rotation is a mechanical mechanism that has a control unit, and it can sometimes get stuck. And this is the most pronounced and the most common failure mechanism of the tracker, that the tracker just gets stuck at a certain position. And so the energy production is suboptimal compared to what would be the case if the tracker would be rotating as it should. So how does this look like? So here are a couple of daily power profiles. So I'm sorry for this, it's not written here, but this is a power normalized to the maximal power possible. So it's normalized between 0 and 1. And this is a profile as function of the time of the day. And here you see a couple of examples of how profiles could look like. Some of them are affected by tracker faults, and some of them here are not affected by tracker faults at all. And I think that just by inspecting them, it's pretty hard to tell which one are the ones that suffer from tracker faults. If you were smart enough, you discovered that these are the ones with the squares are the ones that are affected by tracker faults, and the other ones are not. And let me just tell you that these daily power profiles are the ones I get from single strings. They're not single panels, but they're aggregated power outputs of quite a lot of panels together. They form a structure called a string, and several strings are mounted on a single tracker. So that's the constellation that I'm now trying to detect. So why are these profiles so different? Because the weather conditions can be different, because strings can be differently contaminated, because they can degrade differently. because some of them have faults and some of them and others don't have. So there's a large diversity of profiles, thousands, 10,000s of profiles every day. And I have to be able to tell which profile was affected by a tracker fault at a certain day. That's the task that I deal with. So the way we solved it eventually, let me get the story short because we are nearing the end. So the way we solved it eventually is by taking the operational data from the field and looking at healthy power outputs from the field and coming up with a physical model that can generate, that can corrupt the healthy power output such that it looks like it imitates a tracker fault. And we managed to do that well enough such that we could train a classifier with 50% healthy data and 50% corrupted faulty data, which is completely synthetic. We trained the classifier with synthetic data, and we managed to get very high scores of fault detection. And our baseline in this case was a fully data-driven approach, just an autoencoder that tries to detect anomalies, similar to what I talked about before, just an anomaly detection model. And we compared it to our approach with the augmented data using the physical information. So that's the physics-informed model. And what we realized is that somehow if you look at these confusion matrices, you see that for the same fraction of false alarms, which for a moment you fix, you have much less undetected faults if you use the physics-informed model than if you just use a data-driven approach. This is just setting the threshold somewhere, but we also have a comparison in terms of precision recall plot, which is quite clear. So here you see the precision recall plot, and actually very interestingly, we compare the performance of the data-driven and the physics-informed approach, both on synthetic faults and on real faults. And what we see is that if on synthetic faults, they both somehow perform reasonably well, when you go to the real data, the one that really performs well is the physics-informed. Then the one that fails completely is the pure data-driven approach. So I told you a lot of things today, but maybe from this one use case at the end, maybe 4 points that we actually consider as important in this model is that we had to pre-process the inputs in a very mild way, but important. We exploited the physical model of the fault mechanism, but we used the operational data whenever possible, so for the healthy regime. And another point that turned out being very important, and I did not focus on that, but this can be very interesting for those that want to apply this method, is the induction of physics-informed noise into the data, both the healthy and the faulty. And this really boosted the performance. As you can see, if you want to read this paper from the latest PHM conference, you're welcome to see all the tricks that we used in order to make this model perform so well. So let me just summarize. Now, I was focusing on energy systems because I believe that they are ideal candidates for data-driven methods. They're not the only candidates. We also work with manufacturing systems, and there's a long way to go. We also work with other application fields, but here I see a lot of potential. And I use these examples in order to point out gaps on the way to scalable deployment of predictive and condition-based maintenance. And in particular, I stressed out 4 points, which are dealing with few labeled faults, either by anomaly detection, training on healthy data only, or by augmenting the data using physics. I also talked about scaling up to multi-component systems and to fleet-level algorithms using transfer learning and dealing with problems of data scarcity. So I hope that with that, I gave you some material for thought. If you want to read a bit more, you can, as I said, refer to these 4 papers that I mentioned during the talk, or just contact me. I'll be happy to tell more about that. And here's the link to the tutorial that might be interesting for those who did not attend.